Good morning, sir. I'm Y Nikita from AC Department B section. My roll number is 21951A04C2. My tech talk topic for electrical circuits is Kirchhoff's law. Introduction: Kirchhoff's law, Kirchhoff's voltage law, KVL, analysis circuit of KVL, Kirchhoff's current law, KCL, analysis circuit of KCL. Quiz. Introduction to Kirchhoff's law. History of Kirchhoff's law. Introduction and types of Kirchhoff's law. History of Kirchhoff's law. Gustav Robert Kirchhoff, a German physicist, he described two laws that became central to electrical engineering in 1845. The laws were generalized from the work of George Ohm. It can also be derived from the Maxwell's equation, but were developed prior to Maxwell's work. Introduction. What? A pair of laws stating general restrictions on the current and voltage in an electrical circuit. How? The first of these states at a given instant the sum of the voltages around any closed path or loop in the network is zero. The second states that at any junction of paths or node in a network, the sum of currents arriving at any instant is equal to the sum of currents flowing away. Types of Kirchhoff's law: KVL, Kirchhoff's voltage law; KCL, Kirchhoff's current law. Kirchhoff's voltage law. Introduction to KVL, Kirchhoff's voltage law, mesh analysis, and exercise. Introduction to KVL, Kirchhoff's voltage law. Kirchhoff's voltage law, KVL, is one of the two fundamental laws in electrical engineering, the other being a Kirchhoff's current law. KVL is a fundamental law as fundamental as the conservation of energy in mechanics. For example, because KVL is a really conservation of electrical energy. KVL and KCL are the starting point for analysis of any circuit. KCL and KVL always hold and are usually the most useful piece of information that you will have about a circuit after the circuit itself. Kirchhoff's voltage law states that the algebraic sum of the voltages across any set of branches in a closed loop is zero. That is, sigma V across branches is equal to 0. Below is a single loop current. The KVL computation is expressed graphically in that voltages around a loop are summed up by traversing the loop. Part of traversal. Assumed current direction is the R1, R2, R3. Resulting KVL equation is VR1 plus VR2 plus VR3 is equal to 10, or VR1 plus VR2 plus VR3 minus 10 is equal to 0. The KVL equation is obtained by traversing a circuit loop in either direction and writing down unchanged voltage of each element whose plus terminal is entered first, writing down the negative of every element's voltage where the minus sign is first met. The loop must start and end at the same point. It does not matter where you start on the loop. Note that the current direction must have been assumed. The assumed current creates a voltage across each resistor and fixes the position of the plus and minus signs so that the passive sign convention is obeyed. The assumed current direction and polarity of the voltage across each resistor must be in agreement with the passive sign convention for KVL analysis to work. The voltages in the loop may be summed in either direction. It makes no difference except to change all the signs in the resulting equation. Mathematically speaking, it's as if the KVL equation is multiplied by -1. See the illustration below. Summation of voltage terms may be done in either direction. Paths of traversal. Resulting KVL equation is VR1 plus VR2 plus VR3 minus 10 is equal to 0. Resulting KVL equation minus VR1 minus VR2 minus VR3 plus 10 is equal to 0. For both summations, the assumed current direction was the same. Assuming the current direction fixes voltage references, resulting KVL equation is VR1 plus VR2 plus VR3 minus 10 is equal to 0, and the resulting KVL equation is minus VR1 minus VR2 minus VR3 minus 10 is equal to 0. For both cases shown, the direction of the summation was the same. Mesh analysis. Analysis using KVL to solve the currents around each closed loop of the network and hence determine the currents through and voltages across each element of the network. Mesh analysis procedure. Step 1. Assign a distinct current to each closed loop of the network. Step 2. Apply KVL around each closed loop of the network. Step 3. Solve the resulting simultaneous linear equation of the current loops. Exercise 1. Find the current flowing through each resistor using mesh analysis for a circuit given below. Solution. Assign a distinct current to each closed loop of the network. Step 1. Step 2. Apply KVL around each closed loop of the network. Step 3. Solve the resulting simultaneous linear equation for the loop currents. Step 1. Assume the directions. Step 2. Loop 1, IR1 plus IR3 plus I2R3. I1R1 plus I1R3 plus I2R3 is equal to V1. That is 10I1 plus 40I2 plus 40I2 plus 40I1 is equal to 10. 50I1 plus 40I2 is equal to 10. Loop 2. I2R2 plus I2R3 plus I1R3 is equal to V2. So 20I2 plus 40I2 plus 40I1 is equal to 20. 40I1 plus 60I2 is equal to 20. Step 3. Solving equation 1 and 2 using matrix. 50I1 plus 40I2 is equal to 10. 40I1 plus 60I2 is equal to 20. Matrix form 50, 40, 40, 60, I1, I2, 10, 20. Delta is equal to 50, 40, 40, 50. Determinant of it is 1400. Delta I1 is equal to determinant of 10, 40, 20, 60, which is minus 200. Determination of I2. Determinant of I2 is equal to 50, 10, 40, 20, which is 600. I1 is equal to delta I1 by delta, that is minus 0.143 amperes. I2 is equal to delta I2 minus by delta is equal to 0.429 amperes. From KCL, I3 is equal to I1 plus I2, which is 0.2429 amperes minus 0.143 amperes is equal to 0.286 amperes. Kirchhoff's current law. Introduction to KCL, nodes analysis and exercise. Introduction of KCL. First, Kirchhoff's current law, sometimes called Kirchhoff's first law or Kirchhoff's junction rule, along with the Kirchhoff's voltage law, makes up the two fundamental laws of electrical engineering. 2. In this lesson, it will be shown how Kirchhoff's current law describes the current flow through a junction of a current. 3. KCL helps to solve unknowns when working with electrical circuits. KCL with addition of KVL and Ohm's law will allow the solution of complex circuits. Definition that will help in understanding Kirchhoff's current law. Junction. A junction is any point in a circuit where two or more circuit paths come together. Kirchhoff's current law generally states the algebraic sum of all currents entering plus and leaving minus any point in a junction in a circuit must be equal to 0. So it is restated as the sum of currents into a junction is equal to the sum of currents out of that junction. The algebraic sum of all currents entering plus and leaving minus any point in a circuit must be equal 0. Here the three currents entering the node I1, I2, I3 are all positive in value, and the two currents leaving the node I4 and I5 are negative in value. This means we can also rewrite the equation as I1 plus I2 plus I3 minus I4 minus I5. Nodal analysis. Analysis using KCL to solve for voltages at each common node of the network and hence determine the currents through and voltages across each element of the network. Nodal analysis procedure. Common node, current direction, KCL, solve equation, determine 1 and 5. Common node. Determine the number of common nodes and reference nodes within this network. Current direction. Assign current and its direction to each distinct branch of the nodes in the network. KCL. Apply KCL at each of the common nodes in the network. Solve equation. Solve the resulting simultaneous linear equation for the node. Determine 1 and 5. Determine the currents through and voltages across the elements in the network. Exercise. Example 1. Find the current flow through each resistor using node analysis for the circuit. Remember the steps earlier. Determine the number of common nodes and reference node within the network. Common node and one reference node C. Assign current and its direction to each distinct branch of the nodes in the network. Refer 0 the figure. Apply KCL at each of the common nodes in network. KCL L1 plus L2 is equal to L3. Ten minus VA by 10 plus 20 minus VA by 20 is equal to VA by 40. 1 minus VA by 10 plus 1 minus VA by 20 is equal to VA by 40. VA into 1 by 40 plus 1 by 10 plus 1 by 20 is equal to 2. VA by into 7 by 40 is equal to 2. VA is equal to 11.428. I1 is equal to 10 minus 11.428 by 10 is equal to minus 0.143 amperes. I2 is equal to 20 minus 11.428 by 20 is equal to 0.429 amperes. I3 is equal to 11.428 by 40 is equal to 0.286 volts amperes. Example 2. Find the circuit flowing through each resistor using nodal analysis for the circuit below. Remember the steps earlier. Determine the number of common nodes and reference nodes within the network. One common node VA and the reference node C. Assign current and its direction to each distinct branch of the nodes in the network. refers 0 on the figure. Apply KCL at each nodes of the common nodes in the network. KCL is equal to L1 is equal to L2 plus L3. VA minus 40 minus VA by 5K is equal to VA minus of minus 55 by 3K plus VA by 6K is equal to 40 minus VA by 6K is equal to VA by plus 55 by 3K plus VA by 6K. VA into 1 by 5K plus 1 by 3K plus 1 by 6K is equal to 55 by 3K minus 40 by 5K. VA is equal to minus 14.757 volts. I1 is equal to 10.95 milliamps. I2 is equal to 13.41 milliamps. I3 is equal to minus 2.46 milliamps. Thank you, sir, for giving me this wonderful opportunity of sharing my thoughts.